Okay, this lesson 2B will be about how to compute probability for scenarios involving equally likely cases, and we'll also talk about the idea of odds, which is just a different way to indicate likelihood other than probability. So let's consider what happens if we roll a fair die one time, a six-sided die. So a trial would consist of rolling the fair die one time, and the sample space, which we use a capital S for, is the set of all possible outcomes, which would be 1, 2, 3, 4, 5, and 6. So if we wanted to find, say, the probability of rolling a 3, since 3 is only one of the possible outcomes, it is one of the outcomes, so it isn't impossible. The probability of 3 would not be 0. But it isn't the only outcome, so that means it isn't certain. The probability of 3 is not 1. The probability is going to be somewhere between 0 and 1. And that's what we're going to figure out. How do we assess that probability? Okay, so if you think of this kind of space between probability of 0 and 1 as being all of the available probability, and we know that 3 is just one of 6 possible outcomes on a six-sided die, and if it's a fair die, it means that they're all equally likely to occur, then that means any individual number should get 1/6 of this available probability space, right? So we can say the probability of getting a 3 is 1/6 because it's a sixth of the probability that's available. So another way to compute that, 1/6, would be, well, let's consider that we can list a sample space which has the values 1, 2, 3, 4, 5, and 6. And then we could also create another set which is called the event space that I'm going to use a capital E for, and we'll only list in there the things that relate to the probability we're computing. So if we're getting the probability of getting a 3, then that means the event space would only have the outcome 3 in that. So since there are 6 possible outcomes in the sample space, and there's one outcome in the event space, then you could think of that probability 1/6 as being the number of outcomes in the event space divided by the number of outcomes in the sample space. And in fact, that's going to give us the formula that we use for computing these probabilities. If all the outcomes are equally likely in a sample space, then the probability of the event E occurring would be the number of outcomes in the event E divided by the number of outcomes in the sample space. And a lot of times that's just expressed this way more generally, and it's the number of desired outcomes divided by the total number of outcomes. Okay, so that's going to be our formula for computing the probabilities. And of all the different ways we have of computing probabilities, this one is the one that's usually introduced like in middle school because it's the most straightforward. But actually finding a probability for an equally likely case problem can be either quite easy or it can be very difficult. It just depends upon how hard it is to count the outcomes in the sample space and the outcomes in the event. So let's start with a simple example here. Let's say if you roll a fair six-sided die once, we want to find the probability that you'll get an odd number. So the sample space has the 6 outcomes, 1 through 6, and the event space in this case contains only 1, 3, and 5 because those are the only odd numbers. So using our formula, the probability of getting an odd would be the total number of ways we can get an outcome, which is 6. That's on the bottom of the fraction, and in the numerator it's going to be just the count in the event space, 3. So it'd be 3 out of 6, and therefore that's going to be 1/2. So half the time we would get an odd number. Okay, a second example, also pretty straightforward. Let's say we spin this spinner and we want the probability that the arm will land on green. Well, these sectors seem to be equal widths, equal arc lengths or areas, so that means that each individual sector here should be equally likely. And there are 8 total sectors if you count them up, 1, 2, 3, 4, 5, 6, 7, 8. So the denominator of our fraction here will contain the total number of sections 8. And since we're finding the probability that it will land on green, we want to count up just the green sectors, 1, 2, 3. So the numerator of the fraction will contain a 3. And so the probability of getting a green with this spinner would be 3/8, 3 out of 8. Okay, let's make it a little bit more challenging. In example 3 here, if you roll 2 fair dice, then what's the probability that their sum would be 7? This is a little trickier just because it's a little harder to do the counting. The structure is the same. The probability that a sum of 7 will be rolled is going to be on the denominator the total number of dice rolls, and then in the numerator the number of ways specifically to get a sum of 7. So a great way to deal with rolls of 2 dice is to use a grid. something like this, where we have a two-dimensional thing here where we show across the top in the columns the list of all the possibilities of one dice, and in the rows we'll list all the possibilities of the other dice. So, for example, this 5 here consists of having a 2 on one of the dice and a 3 on the other. Right? This particular 7 right here is a 2 on one dice with a 5 on the other one. Right? This 12 is obtained as a sum if you have a 6 on one dice and a 6 on the other dice as well. So since there are 6 columns and there are 6 rows, there are 6 times 6 blue numbers in here. That's actually the sample space. So that means on the bottom of our fraction over here, the total number of dice rolls is 36. And then if I go back and look at how many of those are actually 7, we can count them up. There are 1, 2, 3, 4, 5, 6, and that's the reason why the top of the fraction has a 6. So it would be 6 out of 36, which reduces to 1/6. So the probability that if we roll 2 dice, their sum will be 7 is 1/6. Okay, now let's go up to the other end of the spectrum and look at a very challenging problem. If you're dealt a 5-card hand from a standard deck of 52 cards with no jokers, what's the probability that the hand will be a full house, which means we have a 3 of a kind plus a pair? Okay, structurally it's done the same way. The probability of a full house will be the total number of 5-card hands we could get, the total number of outcomes, and then on the top of the fraction will be the number of ways that those 5 cards could be a full house. The reason this problem is so much harder is because it's more difficult to count those two things. Okay, so usually it's a little easier to count the denominator, the total outcome. So we're going to start there. We're going to figure out how to count that, and we're going to need to use our more complicated counting strategies. So there's a whole other video, lesson 2a, that goes over these in detail. But just to kind of list them out again, we've got listing out all cases using diagrams, multiplication principle, we've got permutations and combinations, we've got multiplication principle with combinations, and we've got distinguishable permutations. Okay, so if I'm looking at the denominator, total number of 5-card hands, there are 52 cards in a standard deck. We're choosing 5 of them to be in the hand. Each of the cards is distinct. There are no repeats, and we're using up the cards as we put them in our hand. It doesn't really matter what order we pick them, they just end up in the hand. That actually satisfies all the criteria for a combination. So if I go back and look at that, right? We have a set of distinct objects without repeats, choosing some or all. We're choosing some, 5 out of 52. And the objects are being used up, and the order does not matter. So that makes this a combination. So I'm going to use strategy number 4 here to do this problem. And then we're just going to use the combination formula, 52, combination, choosing 5 out of that. And I would just do that in a calculator. So we can bring up a calculator here on the screen and run through how to do that again. We would say we have to put the 52 in, math, probability, and then NCR, choosing 5. So out of 52 cards, choose 5. That is 2,598,960 possible 5-card hands. Okay, so that's going to form the denominator of our fraction. Now we have to figure out the number of ways that we could get a full house. So for the numerator, we need to count the number of ways to get 3 of a kind of one card and 2 of a kind of another card. Now this is the part that's not super obvious. There's actually 4 choices that we have to make, and in making each of those involves choosing some from some cards. So this seems like a good strategy for the multiplication principle with combinations. There's actually 4 choices to make. Here are the choices. First, we have to choose what kind of card are we going to have the 3 of a kind of. Is it going to be 3 kings or 3 sevens or 3 nines? Say we chose 7s. Then the second choice is how many ways can we pick the 3 sevens? And then the third choice is going to be what kind of card will we have for the pair? Will we have jacks? Will we have a pair of 4s? And so on. Let's say we chose jacks. Then the fourth choice is how many ways can we pick those 2 jacks? Okay, so we'll do this one step at a time. To begin with, we'll make a box for each of these choices. We're going to have a box for the number of ways to choose which card to have 3 of a kind of. We'll have a box for the number of ways to choose the cards in the 3 of a kind. We'll have a box for the number of ways to choose which kind of card to have for the pair. And then we'll have a last choice, which is the number of ways to choose the cards that are in that pair. Okay. So, there are 13 kinds of cards in a standard deck of cards. There's an ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, and a jack, and a queen, and a king. So if you just count those up, there are 13 kinds of cards, assuming we have no jokers. And so, Out of those 13 kinds of cards, we have to choose one kind of card to be the one we're going to have 3 of a kinds of. So that means 13 combination 1. And it'll be more reasonable later to explain why this is a combination, but it's a combination, so 13 choose 1 combination. Let's say, for example, that we picked 7s to be the card that we have 3 of a kind of. Okay, so there are actually 4 7s in the deck because there's a 7 of clubs, a 7 of spades, a 7 of hearts, and a 7 of diamonds. So that means out of those 4 specific 7s, we need to choose 3 of them to be in this hand. So that means out of 4, choose 3. We're choosing 3 just from the set of 7s. Right, and now I can explain more why these are all going to be combinations, because once they're chosen, they just end up in the hand. It doesn't really matter if I picked, say, the 7 of clubs first, and then the 7 of diamonds, and then the 7 of hearts. That would still be the same hand as if I picked the 7 of hearts first, and then the diamonds, and then the clubs. So it's a combination, because the order doesn't matter. Okay. So now in the third choice, we need to pick what kind of card are we going to have for the pairs. Right now, we've already, say, used up 7s. That means that there's 12 remaining kinds of cards. There's all that on the list: ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, king, except for the 7s. And so there are 12 cards left to choose 1 of. So 12 combination 1 would be the number of ways to pick which cards to have pairs of. And then the last choice is, now that we know what that is, let's say that jacks are the ones that we're going to have a pair of. There are 4 jacks in the deck, and we have to choose 2 of those to be in there, because a full house consists of a 3 of a kind and then a 2 of a kind. So we have 2 of a kind of the second kind of card. So this is what it's going to be. To compute this, we'll have 13 combination 1, 4 combination 3, 12 combination 1, 4 combination 2. It's the number of ways to make each of those choices. Because we're dealing with multiplication principle, we could do each of those in a calculator to find the combinations: 13, 4, 12, and 6, and then the multiplication principle says we would multiply these. There are 3,744 different possible full house hands of 5 cards. So finally, we can build our probability fraction, right? On the bottom, we found that there were 2,598,960 different 5-card hands, and then we were able to count that there are 3,744 full house hands. So 3,744 out of the 2 million gives a probability of 0.00144. So the probability of getting a full house dealt to you when you have 5 cards is extremely low. It's only 0.14%. That's why a full house is worth so much in the game of poker, because it doesn't occur naturally very often. Alright, so that example was about the very limit of the hardest kind of a equally likely case probability we would have. Something where it requires multiple strategies to count the numerator and the denominator. But really all 4 examples you can see are kind of the same structure, right? Alright. So, before we end this lesson, we had to talk about somewhere the difference between odds and probability. So we decided to put it in here. Just odds are another way to indicate how likely something is to occur. Probability for equally likely cases is found using a fraction. It's the number of desired outcomes divided by the number of total outcomes. If you have a situation where there's only 2 possible outcomes, and you can label one outcome as success or yes or winning, and the other one as no or failure or losing, then you could think of the probability fraction as just simplifying down to this. The probability that we win is the number of ways to win divided by the number of total outcomes, right? But the number of total outcomes is the number of ways to win plus the number of ways that we lose, okay? This may become a little clearer when we do a specific example. So probability of winning is the total number of things that can happen, which is winning plus losing in the denominator, and on the top it's only the number of ways of winning. Okay, so the probability is really the fraction of the total outcomes, which are the wins. Okay, there is a different way to express how likely a win is to occur. Instead of comparing the number of wins to the total number of outcomes, you could compare the number of wins to the number of losses instead. So if you express likelihood this way, it's called giving the odds. And this is usually written as a ratio horizontally. So the odds of winning are written this way by listing the number of ways to win and then a colon, and then the number of ways to lose. And you can also express the odds against winning by reversing the numbers. Odds against winning are the number of ways that we can lose, colon, number of ways to win. Okay, it's easiest to understand this by looking at some specific examples. So let's say that you and a friend have played 10 games of one-on-one basketball. You've won 6 of the games, and your friend has won 4 of the games. So the probability of you winning a game would be, out of the 10 games, the wins plus the losses, 6 of the times you won, so it would be 6 out of 10, or 60%. Right? That would be the probability of you winning. But if we wanted to express it as odds, it would be the odds for you winning are 6 to 4, which is read 6, and then the word 2 is used when we talk about that little colon. So it would be read 6 to 4, which means you'll win every 6 games for every 4 that you lose on average. The odds against you winning are 4 to 6. So it's just kind of a different way to think of it, right? Probability is the number of wins, right, divided by the total number, and odds are the number of wins compared to the number of losses. Okay, so to convert from probability to odds, let's say we have probability of winning is 60%. You could convert the decimal to a fraction with some reasonable denominator. So if you have 60% chance of winning, you could write that as 6 out of 10. And then you could subtract the numerator from the denominator to get the number of losses. So if we know there are a total number of 10 outcomes and 6 of them are winners, that means 4 of them are losses. And then you can rewrite it in the other way. Probability of winning 60% means the odds are 6 to 4, the number of wins to the number of losses. If you want to go the other way around, you want to convert from odds to probability. If you're given that the odds for winning are 6 to 4, then you can add the total wins and losses together to get the total number, and then re-express it as a probability, which is the number of wins divided by the number of losses. Okay? So it's just 2 different ways to write the same thing, likelihood. Honestly, I prefer probability because I think of it as a percentage, and the higher the percentage, the more likely it is. But odds are used frequently, especially in gambling scenarios. Okay, to summarize what we covered in the video, first of all, we said if all outcomes are equally likely, then the probability is always going to be the number of outcomes in the event space divided by the number of outcomes in the sample space, which you can think of as the number of desired outcomes divided by the total number. And finding probability for equally likely cases can either be very easy or very difficult, just depends on how hard it is to count. And then for odds and winning, the probability is the number of wins over the total number, but the odds for winning is the number of wins to the number of losses. So you have to figure out the number of losses. Okay, that's it for this topic. You can move on to other topics to explore the rest of probability.